Today we're talking about section 4.1, which is extreme values of functions. We're going to talk about how do we find the global extremes and the relative extremes. So we've called these minimas and maximas in pre-calc, and then this is your absolute min, your absolute max, the global maxes and mins. So the first place they start is the global, a function that has a maximum or a minimum. So the definition says if f is a function with domain D, then the absolute maximum value on that domain happens when the rest of the function is smaller than a certain value. So if we were to kind of sketch a picture of what that looks like, we're saying, all right, here's this function. Everything on this function is smaller than this point c f of c. So that makes this one a maximum value. The converse is true, so if I flipped that around, then if the function is always bigger than some value, and I like using the parabola, it does not mean it has to be a parabola, then that would be considered a minimum value. So your absolute min and max values are called your absolute extrema. If you look in your textbook and you're looking at a question, and if it just asks for the min and max or the extreme values, usually they'll omit the word absolute. So if you see max and min, they're talking about those global values. So in example 1, it's not really a question, just more of an illustration. So it says on the interval from negative pi halves to pi halves, f of x equals cosine of x takes on the maximum value of 1 once and a minimum value of 0 twice. So when I'm doing cosine from negative pi halves to pi halves, that function, when I graph it, negative pi halves to pi halves, cosine is the one that starts up here at 1, and so it comes down, and then it continues on, of course, but we're only looking at this window. So here's your maximum value at 0, 1, and then your minimum value on that closed interval, notice it has the brackets, so it's equal to, is at pi halves 0 and at negative pi halves 0. And then it walks us through the function sine of x. Well, sine of x looks very similar to cosine of x, negative pi halves to pi halves, except this one goes through 0. And so that one looks a little bit different. So you'll notice the maximum value is up here at 1, and the minimum value is down here at negative 1. So here are 4 different representations of y equals x squared. I want you to take a moment and I want you to look at the domain that they've given you and find the max and min value for each one. I want to start with all reals. Y equals x squared over the entire interval. The minimum is at 0, 0. That's where our vertex is. And there is no maximum because this one goes up forever. Now part B, they limit our window and they say, well, what if we go from 0 to 2? If I start at 0 and go to 2, that's half of a parabola. Starts here, goes up to here. And it includes both of those endpoints. So my min is at 0, 0, and my max is at 2, 4. But then when we move to part C, they put a curvy bracket on 0, which means it doesn't include 0. So when I graph that, it still looks absolutely identical to what we just did in part B, except there's a hole at 0. So this time there is no minimum because you can keep getting closer and closer and closer to 0. You just never actually get there. So there is no minimum value. And then that means for 0 to 2, when you don't include 0 or 2, we're going to have a hole on both ends, which means I can't have a max or a min. So the extreme value theorem is a really important theorem, and it says if you have a continuous function, that's our first condition, on a closed interval, from A to B, then you are guaranteed that f has both a maximum and a minimum value. And I'm going to just kind of refer you back to letter B. In fact, I would put a star next to letter B. That's the only one we were guaranteed to have both a max and a min because it was continuous on a closed interval. This is one of those big theorems that shows up on the AP exam. This is one that you're going to have to cite. When they say justify your answer, extreme value theorem is one of them that you're going to have to remember. So that's for global maxes. So what happens if we're talking about functions that have local max and mins? Remember, local maxes and mins are the types where we have a function that kind of goes all over the place. Looks kind of one of those. This one wouldn't have a global max or min because it goes down forever and it goes up forever. But we've got all these little places here that we need to consider because the function is changing directions at these places. So they're important values as well. So it says we have local maxes if the function is smaller than a particular function value on an open interval. So like this would be an open interval, and there's a maximum value there. Here's another smaller interval with a maximum. The opposite is true for the minimum, so there would be a min, and there would be a min. Sometimes you'll see it referred to as relative extrema. Now, the important thing for checking for all of these extreme values is this local extreme values theorem. And it says that your function f has a local max or a local min at an interior point, and the derivative exists. This one is important. That means it's differentiable. If that derivative exists, then f prime of c is 0. That means the slope of the tangent line at all of these points is 0. The important thing here is that that derivative exists. If we have a corner or a cusp or something going on there, that's going to be something different that we're going to talk about. That's right here, the definition of a critical point. This one, I want you to please highlight, put glitter all over this one, smiley faces, stars, something. This is the most important definition of this unit. And it says a point in the interior of the domain of a function where the derivative is 0 or the derivative does not exist. There's your two conditions. If one of those things is happening, we call it a critical point. So not only do we have to check where the derivative is 0, we also have to look for things like vertical tangents, cusps, corners, and any discontinuities. Those are all potential maxes and mins as well. So example 3 says we're going to find the max and min values of x to the 2/3 on this interval.